Hey guys, welcome back to part 2 of our video on section 8.3, vectors. So we talked about what a vector is. We talked about writing it in component form and stuff like that using those kind of angle brackets. Now we want to talk about standard unit vectors and how we can write vectors in that form. And so very simply, we talk about standard unit vectors being two different vectors. Okay, so if we have our xy coordinates like this, then we have the vector I and the vector j. Okay, the vector I is very simply the vector that is 1 unit in the x direction and no units in the y direction. The vector j is the opposite. It's no units in the x direction, 1 unit in the y direction. So what these basically represent is kind of our 1 unit to the left, 1 unit up. And by multiplying these with scalars and adding them together, we can write any vector we want using these standard unit vectors. So let's look at this example here. We are told that given the initial point -6, 5 and the terminal point 3, 2 of the vector u, write u using the standard unit vectors. So the first thing we want to do is we want to write this in a way that is the most convenient, right? So if you remember back to part 1 of this video, that means writing it so that the initial point is at the origin and the terminal point is wherever that may be. And the way we can do that is we simply say, okay, well, that means that u, the vector u, is equal to, and we take the x value of the terminal point, subtract the x value of the initial point, and then take the y value of the terminal point and subtract the x value of the initial point to get our resulting vector, in this case, 9, -3. Okay. If we split this, right, we can think of this as the vector 9, 0 plus 0, -3. So then using scalar multiplication, just kind of the same way we could factor anything out, we can say that this is 9 times the vector 1, 0 minus 3 times the vector 0, 1. And since the vector 1, 0 is exactly I, we'd say this is 9i. And the vector 0, 1 is j, so minus 3j. So that is the way that we can write this. And it's always a good idea to acknowledge that these are vectors. It's given the context, if I say, write something in a standard unit vector and you said 9i minus 3j, I know exactly what you're talking about. It's not a big deal, especially if you're trying to type in an answer or something like that. Trying to get that vector markup there. I don't know if there's an easy, quick key for that in the drop-down menu when you click into the box. But if you just type 9i minus 3j, that should be good. So let's look at our next example. Okay, this combines a few things. So it wants us to find a vector v given its magnitude and pointing in the same direction as u. So we're told that the magnitude of vector v needs to be 3, and it needs to be in the same direction as this vector u, which is -12, -5. And it wants us to write our answer using these standard unit vectors. So the easiest way to do this is to find the unit vector in the same direction as u. And since we want the magnitude of v to be 3, we know the magnitude of the unit vector would be 1. And so if we find the unit vector in the same direction as u, multiply by a scalar of 3, that will give us our vector v. And then we just have to convert that into the standard unit vector form. So to do that, the first thing we need to do is find the magnitude of u. So the magnitude of the vector u is the square root of -12 squared plus -5 squared. Now, for those of you that are recognizing this as one of those special right triangles, absolutely correct. You probably already know what the magnitude is. For those of you that don't, let's find it. So 12 squared is 144 plus 25 gives us 169. The square root of 169 is 13. So that means the magnitude of u is 13. So let's say the vector w is equal to 1/13 v, or sorry, not v, u, the vector u. So that means it is simply negative 12 13ths over negative 5 13ths. So that means w is the unit vector that is going in the same direction as the vector u. So now what we need to do is, that means that v, the vector v, is equal to 3 times the vector w. Just 3 times negative 12 13ths, negative 5 13ths, which is equal to negative 36 13th, negative 15 13ths. Okay, so now to write this in standard unit vectors, we could do the same thing we did here, where we split it to be like 9, 0, 0, negative 3, factored out. But we can also just see that what happened is I just took the component that's in the x, multiplied it by the I, took the component that's in the y, and multiplied it by j. And so we can do that same thing here, and we end up with negative 36 13ths vector I minus 15 13ths times the vector j. And that's it. That is as easy as this problem gets. So because we wanted it to have a magnitude of 3, be in the same direction as u, now you could say, well, why didn't we just say, instead of doing this unit vector w, why didn't we find the magnitude of u and then multiply by 3/13? And that would absolutely work. But it just kind of makes it so it's kind of a little bit skipping steps, and it may be a little less obvious why we do that. But doing this way kind of really breaks it down for us. We can see where all of these pieces come together. So we've talked about finding all these magnitudes. We've talked about these things being in the same direction. Now we want to actually talk about, how do we figure out what that direction is, other than just doing things like unit vectors and stuff like that. Can we use trig to help us out? And the answer is, of course we can. So and I have in this drawing this vector v. Okay, and I'm going to label this here. So we do this. So that means this distance here is v1. This distance here is v2. And this distance here is the magnitude of v. So we have a right triangle, right? So the angle from this vector measured in standard position, right? So we are taking a vector that is at initial points at the origin. If it's somewhere else, move it so that it's at the origin, and then we can do this really easily. And then we talk about its angle in standard position. So what's cool about that is, because we're talking about its angle in standard position, we can say that 0 is less than or equal to theta is less than or equal to 2 pi, or 0 degrees is less than or equal to theta is less than or equal to 360 degrees. And actually, really, we don't want that. It's just less than. Because if it's equal to 2 pi, we would just say it's 0. If it's equal to 360, we would just say it's 0. So to find theta, we can just use tangent, because we know the components of this vector. We know v1, v2. That means that tangent of theta is equal to v2 over v1. I don't like how far down that came. Let me just rewrite there real quick. Tangent of theta is v2 over v1. That implies that theta is equal to inverse tangent of v2 over v1. Okay. Now we have to be careful with that because, and I'm going to say, yeah, I'm going to leave it like this, but I'm going to put a little asterisk. Be careful, since inverse tangent of x is in negative pi over 2 to pi over 2. So when you're doing this, you may have to, if we are giving you some vector, you may have to kind of think, let's say I give you this vector here, and I say, what's this angle? Well, when you do inverse tangent, it's going to give you this negative angle. And so you'll have to figure out what the actual correct angle is. Okay, so make sure you guys are being careful, not just using inverse tangent and saying, that's it, we're done, move on. Okay. Now what's really cool is from this triangle, we get a couple of other really nice facts. We get that cosine of theta is equal to V1 over the magnitude of V, which means that V1 is simply equal to the magnitude of V times cosine theta. And we get that sine theta is V2 over the magnitude of V. And so V2 is simply equal to the magnitude of V times sine theta. And there we have it. So those are some really nice, cool, useful facts, right? So I'll just rewrite that over here. V1 is equal to the magnitude of the vector V times the cosine of theta, and V2 is the magnitude of vector V times sine theta. And if you remember from the unit circle, cosine gave us the kind of x value, sine gave us the y value, and it really kind of still continues to apply here, where if we think of the components of a vector being like the kind of x comma y, the x component is brought to us by the cosine, the y component is brought to us by the sine. So very nice and simple. So another definition. The horizontal and vertical components for a vector v equaling a1, a2, having direction angle theta, are given by exactly what we just talked about. So a1 is the magnitude of v times cosine theta, a2 the magnitude of v times sine of theta. So v is the magnitude of v times cosine theta, comma, magnitude of v sine theta. Okay, or if you want to write this in standard unit vectors, right, we could say the vector v is the magnitude of vector v times cosine theta times the vector I plus the magnitude of v times sine theta times the vector j. Whew, whole lot of this stuff there. All right. Here's what we really care about, right? Here's what you really want to know, how we're going to have problems with this. I want to find the direction angle for this vector v given in standard unit vector form. The first thing that's really important is to give yourself a picture. Draw out what this looks like. Okay? And the reason why this is really important is because it helps you to identify what quadrant this is in, and it helps you to take these inverse trig functions and correctly apply them to get an angle between 0 and 2 pi. So we're at 2, so our x value is 2, or y value is negative 6. So our vector is somewhere around here. So this is our vector v. I need this angle here. So this is my angle theta. So what I know is I know that tangent of theta is equal to negative 6 over 2, which means we are looking at tangent of theta equals negative 3. So if you remember, when we could do these things, right, we would get like reference angles and things like that. Instead of a reference angle exactly, I'm just going to call this theta 1. theta, what is it giving me that? Theta 1 is equal to inverse tan of -3. So theta 1 is going to be this angle here. Theta 1. And when we use our calculator, right, you need to identify whether you want to be in degrees or radians. We get that theta 1 is approximately, so this is a really important thing to make sure your calculator is in the right mode. I can't emphasize that enough. Mode on your calculator is a very, very, very big deal. Okay, so it's approximately -1.249 or -71.565. Okay, so that is our theta 1, right? Which, as I've got drawn on here, maybe a little poorly, is this negative angle here. But I need the positive angle. And what's really nice is because if we add them together, we get a full rotation. So that means that theta is equal to theta 1 plus 2 pi, or theta 1 plus 360 degrees. I forgot to put that little degree up here. So let's add these. So we get that theta is approximately equal, because we don't want to say it's exactly equal. .034 or 288.4 degrees. So depending on what the question specifies, whether it specifies to give your answer in radians or degrees, make sure you follow that directions and do it that way. But that's it. Pretty straightforward and simple, right? So using these ideas here, right, that tangent of theta is V2 over V1. It means theta is tangent inverse of V2 over V1. Remember, be careful. You want to make sure we're using the right quadrant. We saw that in this problem here. So we want to find the component form of the vector v, given that the magnitude of v is 7/2 with a direction angle of theta equals 150 degrees. So we are in degrees, so that means we want to make sure our calculator is in degree mode. So if you have been switching around or not, you're not sure, check, double check, triple check, make sure you're in degrees. Well, very simply, by following this definition 4 up here, we get that the components are magnitude v times cosine theta, magnitude v times sine theta. So that means that the vector v, why is it not? The vector v is equal to the magnitude of v times cosine theta and the magnitude of v times sine theta. So the magnitude of v is 7/2 and theta is 150 degrees. Okay, and you can use either the unit circle, or you can simply use your calculator if it doesn't tell you to give exact answers. We like exact answers here, so we're going to use the unit circle because we know 150 degrees is on the unit circle. So, we have 7/2. Cosine of 150 degrees is -√3/2. We have 7/2, and sine of 150 degrees is just 1/2. And so this just becomes -7√3/4, comma 7/4. And there we have it. That's it. So that is something that's really important. So these ideas right up here, okay, from this definition 4 would be definitely something you want to have on that quick sheet, right? That the kind of x component, the a1, is magnitude of vector v times cosine of theta. A2, the y component, is magnitude of vector v times sine theta. And that tangent, or that theta is equal to the inverse tangent of v2 over v1, or a2 over a1, depending on what variables you're sticking with. So make sure you have that written down. Now, this next thing, if you're looking ahead, you might be able to guess what this word is. Okay, the dot product. So with numbers, and even with vectors, we have the idea of addition, subtraction, multiplication, division. If you remember back to Math 111 and functions, right, we had function composition was this kind of new thing that we could do. Dot product is a new thing that is specific to vectors, okay? And the dot product of u and v is going to give us a scalar number, or a real number. So it's not going to give us a vector. The dot product will give us a single numeric value. And we say that u dotted with v, and there's a couple of different things here. We don't really want to use a big open dot because that looks like composition. We want to kind of do like this. And we don't really have multiplication of vectors. We can multiply a vector by a scalar, but we don't multiply two vectors together. What we do is the dot product instead. And so that results into this. And so another way you could write this, right, is component-wise. So you could say u1 comma u2 dotted with v1 comma v2. And what that simply is we multiply the component, the corresponding component, so u1 times v1, and then we add them together. u2 times v2. Okay, and so if we notice, we took these numbers, these number components, multiplying them together, which gives us a number, and then we add them together, which gives us just a number. Okay, so let's talk about some quick properties before we actually dive in and actually do some things with the scalar. So property 1, u dot v is the same as v dot u. And that is how we say it. We say the u dot v, right? Or you could say the dot product of u and v. Either way is acceptable. Any vector dotted with the 0 vector is going to give you the scalar 0. If I am dotting a vector over vector addition, I can distribute that. So that is the same as the vector u dotted with the vector v plus vector u dotted with vector w. What's really kind of cool here is if I dot a vector with itself, that's simply equal to the magnitude of that vector squared. And lastly, if I have a scalar multiplication times the dot product of two vectors, I cannot distribute that to both, right? It's not like addition, but I can assign it to either one. So just like if I have A times B times C, that could be A times B times C, or we could even flip things around and say that's B times A times C, right? Same thing here. So C times U dot V is going to be C times U dotted with V, or U dotted with C times V. Okay, so in this case, C is a scalar, so C is a singular number. So let's look at these example 11 problems here. We've got 3 of them, and I want to simply find these dot products. So if U is the vector 4, 5, and V is the vector 0, negative 2, okay, U dot V is equal to 4, 5, dot 0, negative 2. I'm not going to write that out every time, but I just want to do it this first time. So then the dot product is the x component times the x component. So this is 4 times 0 plus the y component times the y component. 4 times 0 is 0. 5 times negative 2 is negative 10. So we get negative 10. Again, I'm writing more stuff than we need to, but hey. So the next one is asking us v dot u. Now, we know by property 1, this should be negative 10. But I want to make sure, just do it again and see what we get. So again, right, this is u, this is v, which is 0, negative 2, dotted with v, which is 4, 5. Component-wise multiplication, so we have 0 times 4 plus negative 2 times 5, 0 minus 10, not 100, 10, which is negative 10. And hey, look, those are the same, matches the property, we feel good. Magnitude, or u dot u, okay? So that means we have 4, 5, dotted with 4, 5. Okay, so that's component-wise. So we have 4 times 4 plus 5 times 5, which is 16 plus 25, which is 41. Now, let's find what is the magnitude of the vector u. All right, well, that's the square root of 4 squared plus 5 squared. And we can see right there, we have 4 times 4 and 5 times 5 over here, but we don't have the square root. How do you get rid of a square root? You square it. And that's why if we dot a vector with itself, it's equal to the magnitude squared. Okay? So, feeling all right? Okay? So here, we have two vectors, A and B, and it's asking us to calculate the dot product of the difference of the vectors. Now, there's a lot of shortcuts we could jump around to here, but I want to go ahead and do this all together for no other reason than it just kind of gets us some practice manipulating these things and working around with these things. The first thing we need to do is we need to find what is A minus B. Okay, well, the vector A minus the vector A minus the vector B is simply equal to A1 minus B1, A2 minus B2. Right? Just component-wise, very simple. So that means that vector A minus vector B dotted with vector A minus vector B is going to be A1 minus B1, comma, A2 minus B2, dotted with A1 minus B1, A2 minus B2. And that's just component-wise, right? So we have A1 minus B1 times A1 minus B1 plus A2 minus B2 times A2 minus B2. Do some fancy distributions, and we get A1 squared minus 2A1 B1 plus B1 squared. Okay, and that's just basic x plus y quantity squared FOIL results. Hopefully you guys are comfortable with that. And then for this other part, we get A2 squared minus 2A2B2 plus B2 squared. Okay. Do a bit of fancy rearranging here. You have A1 squared plus A2 squared plus B1 squared plus B2 squared and minus 2A1 B1 minus 2A2 B2. Now the reason I did that is because this and this give me two nice little things. What they give me is they give me the magnitude of A squared plus the magnitude of B squared. Okay. And then minus 2 a1 b1 plus a2 b2. Now you may be wondering, how did that become plus, right? We had minus 2 a1 b1 minus 2 a2 b2. But if you notice, I factored out a negative 2, which makes the a1 b1 and a2 b2 both positive expressions. Okay, so I did two things here. I recognize the fact that a1 squared plus a2 squared is the magnitude squared of a. And then I factored out the negative 2. And so if we're careful, we can see that a1 times b1 plus a2 times b2. So we have our magnitude of a squared plus our magnitude of b squared minus 2 a dot b. And that's it. So if we take the dot product of the difference of two vectors, that becomes the sum of the squares of the magnitudes of each vector minus 2 times the dot product of the two vectors. Super obvious and clear thing. Not really something we're going to use a whole lot, but it wouldn't be a bad thing to have written down somewhere you can quickly access it and stuff like that. I was really more focused on just kind of that practice of doing this with maybe a more messy situation, something that's all variables and not just a bunch of numbers, because numbers are pretty quick and easy. We're comfortable with that. I want to make you uncomfortable in here so that way you're not uncomfortable in the homework later. Okay, so take that as just kind of this algebraic manipulation practice. If you're going to go on and take calculus, that's something you need to be very comfortable with, is the material that we just did, what we just did there, all of that manipulation should be something that you should be very comfortable with if you're planning on going on to calculus. If you're not comfortable with that, go through it a few times, pause the video, do it yourself until you get comfortable with it, okay? All right, now what about the angle between two vectors? So what I mean by this is if I have, let's say, vector A and vector B, I want to find this angle here. And what's cool is if I do this, this is actually A minus B. So how do I figure these out? Okay, I don't really want to derive this with you guys. I just want to give this to you guys. Save us all some time and headache. Theta is equal to the inverse cosine of the dot product of the two vectors divided by the product of their magnitudes. Okay, so if we take the dot product of two vectors and then divide it by the magnitude of each vector, the product of the magnitude of each vector, and then the inverse cosine of that, that gives us our theta value. Okay. Again, we want to be careful, right? If these things are really crazy far off, we may need to worry about some issues with the range of cosine, but for the most part, you're not going to get anything too crazy because we're not worried about standard position here. So since cosine goes from 0 to 180, if we have, say, two vectors that are like this, then that's going to be our angle. But if we have two vectors that are like this, well, then that's our angle between. So we don't really have to worry about it, actually. So let me backtrack. We don't actually have to worry about the range of cosine, of inverse cosine. It just gives it to us, very simply. Okay. So vectors A and B are, and this is a big fancy word that we're going to use here, orthogonal which just simply means perpendicular, if and only if their dot product is 0. And so think about, what does it mean to be perpendicular? It means very simply that you intersect, so these are our two vectors, at a 90-degree angle. The only way that the inverse cosine gives us a 90-degree angle is if it's the inverse cosine of 0, because we know cosine of 90 is 0. And the only way this quotient here, this a dot b over a magnitude of a divided by magnitude of b, the only way that will be 0 is if the dot product of a and b are 0. Okay. Now, there is one notice here in the definition: two non-zero vectors. So neither a or b they can't be the 0 vector. Problem is then we're dividing by 0. That's a problem. It's bad. So, normally I would go through and prove this and derive this idea for you guys. And it uses the difference of vectors dot product, but I don't want to. Okay. The very simple reason I don't want to is it's unnecessarily messy. Okay. So I'm going to say here, we're going to skip the derivation of this. So derivation is where it's derived from, where it comes from. Instead, let's just do an example. Okay, so remember, theta is equal to the inverse cosine of the dot product of the two vectors divided by their magnitudes. So we want to find the angle theta between this vector u and vector v. So what we have to do is we have to find the dot product of the two vectors, and we have to find the magnitude of each vector, and then move from there. So let's start with the dot product. Come on. Okay, there we go. So, okay. So u dotted with v is equal to, so I'm not going to write out these vectors. I'm just going to write out their component multiplication. So it's equal to 4 times 2 plus 3 times negative 5, which gives us 8 minus 15, which is negative 7. Woohoo! Now the magnitude of vector u is the square root of 4 squared plus 3 squared, which is the square root of 25, which is 5. The magnitude of v is the square root of 2 squared plus negative 5 squared, which is the square root of 29. And that doesn't give us anything nice, so there it is. All right, we now have our 3 components to find the angle between these two vectors. And we just grab our calculator, and we say theta is equal to inverse cosine of the dot product, negative 7, over the product of their magnitudes, 5 times root 29. Notice this didn't give us whether it wants it in degrees or radians, so it really doesn't matter. Let's get this typed into our calculator, negative 7 over 5 root 29. And so we get that theta is approximately equal to 105.068 degrees, or if we go to radians, 1.834. Okay. Make sure that you guys are paying attention to what the question is. I guarantee you on all the homeworks, it specifies which one, or at the end of the answer box, you may see like a little degree symbol, in which case it should be in degrees, right? So make sure you're paying attention to the problem. Don't just assume that it's radians or degrees. Check what you're doing, okay? We are almost done. We have a page and a half left. One more example and one more idea. So are these two vectors orthogonal? So what does it mean for two vectors to be orthogonal, right? If you remember, if you recall, two vectors are orthogonal if and only if their dot product is 0. So we just simply need to check, is u dot v equal to 0? Well, u dot v is 4 times 12 plus negative 6 times 8. And we get a lovely 48 minus 48, which that's equal to 0 in my book. So that means, yes, these are orthogonal. Okay. One last thing, and then we are done with this lesson, and that is work. When I talk about work, I'm not talking about your homework or the work you do for a job. I'm talking about the amount of physical work that is being done. So we say if a force is applied to an object in the direction the object moves, then the work done is simply defined as W, the work, equals the force times the distance. So what this simply means is, imagine, if you will, we have a box. It is being pushed this direction, let's say 10 feet, and we are pushing it in that direction with a force of, say, 5 feet. So in that case, then the work done is simply equal to 10. Sorry, not the work. The force isn't 5 feet. The force is 5 pounds. So we have 10 feet times 5 pounds. And that's equal to 50. And then the units of this is foot pounds is how we read it. We abbreviate it, FT. OBS, foot pounds. Now, what if it's not in that same angle? Or not if it's in the same direction. So this was, notice that 5 pounds is going exactly to the right, move it exactly to the right. What if our object is moving this direction? Let me make that a little longer. But it's the force being applied is in this direction. So this is our force, and this is the distance. Okay. That's right here is theta. Okay. What we can do here, right, is we can figure out that the work being done is, so essentially what force is being applied in the exact direction that we're moving. Well, that's very simply, right? If you want to, we can say that this is the x component, right? Which is the magnitude of F times cosine theta. Okay. So that means the work being done here is the magnitude of the distance we are moving, because that's how far it moved, times the magnitude of the force vector times cosine theta. And now we're going to do something a little crazy, and we're going to show that this is just simply the dot product of F and D. And it relies on, if we scroll back up, okay, that theta is the inverse cosine of the dot product divided by the magnitude, which means we can kind of, instead of taking the inverse cosine, we can leave it as cosine of theta is the dot product of over the product of their magnitudes. So this is using the fact that cosine of theta is equal to vector A dotted with vector B over the magnitude of A times the magnitude of B. We get that simply by taking the cosine of both sides, right? And that cosine of the cosine inverse gives us just what we had, and cosine of theta. So I can use that to say that I have the magnitude of the force vector, or of the distance vector d, times the magnitude of the force vector F, times, instead of cosine theta, it's times vector d dotted with vector F all over the magnitude of d times the magnitude of F. And very simply, those cancel out. And we get that this is d dot F. So that means the work is equal to vector d dotted with vector F. It's pretty nice. So let's do an example like that. A wagon is pulled 500 feet using a force of 10 pounds applied to a handle, which makes a 40-degree angle with the horizontal. Calculate the work done. So what I have here, is I have a wagon. It's a pretty terrible wagon. It doesn't even want to automatically do it in the square. A wagon. It's got a handle. And this angle here is 40 degrees. And I know the magnitude of this force is 10. And this distance vector here has a magnitude of 500. Okay, so in this case, we don't necessarily just want to use the dot product, but we could if we had these two vectors, if we had vectors representing these. Here, what we want to say is that the work being done is the magnitude of d times the magnitude of F times cosine of 40 degrees. We're going to use the generic cosine of theta, which that is just 500 times 10 times the cosine of 40 degrees, which is equal to, so 40 degrees, not on our unit circle. So we need to make sure we are in degree mode. And then we can just simply type this into our calculator. And we get that the work done is approximately 3,830.222 foot-pounds. So let me make a correction up here with our unit. There's like a little dot here for foot-pounds. That's it. So that's how we calculate work. If you're given two vectors, let's say, so here we could be given the vector for D would be 500, 0. This is vector D. The vector F, I believe, so is about 7.66 comma 6.428. So if we took the rough dot product of these, we would get what we're looking for. Okay, I'll leave that to you to check. And that is it for our lesson today. Hope you enjoyed learning about vectors and all of their fun intricacies. Make sure you go on and do the homework on this, and I will see you guys for 8.4.